Okay, so here we are for Monday. In case you happen to watch this from home, we're going to do a little lesson today on buggy car data, and you're going to help me do some timing. So here's the deal: we're going to take this car, and you're going to time it, and then we're going to record this data right here. Okay, this is 1 meter. You're gonna time this for me. Are you ready? This is a horrible car. Try this one. Are you ready?
Right away.
Exactly. So I'm going to turn this thing on. You're going to stop it. You ready? 3, 2, 1, go. Stop. Did you get it?
I went from 20 to 80.
Oh my gosh. Let's try this again. You're going to start it right at the beginning of this thing. Are you ready? 3, 2, 1, go. Stop. What did you get?
3.62.
3.62. So 2.62, even better. Now what we're going to do is we're going to take that car. We're going to take that car. I'll change that to red. I'm a trained professional. I'll be here all day. If I were to take a snapshot of this thing every half a second, just take a picture of it, would you guys agree that that would look sort of like a dot diagram would sort of look like that? Would you guys be in agreement? If it's a constant speed car that travels equal distances in equal times, that would be sort of like a dot diagram for it. What you said is that it took how much? 2.62 seconds. And the distance that it traveled, we said was 1.0 meter. So 2.62 seconds, 1.0 meters. Now, if that's x is equal to 1.0, this x is equal to 0. I might call that x initial. I might call this x final. So I changed my position from 0 to 1 meters in that much time. If I wanted to calculate the speed of that car, it'd be no different than the velocity of that car because I'm not really changing my direction. I would just use an equation that looks like that. We'd say that it travels 1 meter, and it did that in 2.62 seconds. I take a ratio of those two things, and that's just going to give me the speed. 1 divided by 2.62 tells me that that is 0.382 meters per second. Did I do that right? Are you okay?
Yep.
Now, you mentioned sig figs. If this is what I'm doing, and I go through all that calculation, if that's 1.0 and that's 2.62, I'd round that to what? If I'm using sig fig notations, what would we do? 1.0 divided by 2.62. It'd be 0.38. Now, I don't really care that much whether or not you get that exactly to 3.38 or 0.382. What I wouldn't want is for you to write 20 decimals there because that's what my calculator says like that. So usually when we're doing a division kind of thing, we go to the number of sig figs of these values. That has 2, that has 3. I put my final answer in 2. The least number of sig figs that I have in any of the values. Okay, now that doesn't mean it's a constant speed. That's an average speed. But if I were to, and I had you guys test this, right? I'm like, well, let's have you guys test this thing over multiple intervals to determine that it truly is a constant speed. I could have gotten the exact same average speed by having the car do something like this and travel the same amount of distance in the same amount of time, but it could have been a changing speed, right? So just because it's constant, or because it's constant, that value is the same throughout, whereas I could have had something where it just traveled at a different rate at different times and I still got the same value. Okay? Now that's a buggy car. Now what I'm going to do, we're going to try this again. Okay, now what I'm going to do is I'm going to have you guys need to help me with this. Car's going to go along here, and I'm going to have you make a turn. So I need some, can you give me a little bit of,
Yeah.
get that stuff out of the way. Yeah. Out of this one. What we're going to do is we're going to have the car come to the end of this thing 1 meter, and then we're going to turn it. And Eddie,
Yeah.
is that how it is?
Yeah.
You are going to make the turn, and you're going to allow that thing to turn like that. And we're going to do this exact same thing. Are you okay with this? You know what we're doing? Okay. I need some more meter steps. Can you go? Oh, thank you. Yep, thank you. Are you ready? This is super exciting. Okay. You see what you're doing? Car's going to go along here and make the turn. I need more space. To there. You're going to make the turn.
Oh, I am?
Yeah, you're going to make the turn.
I'm just grabbing it.
Yep. Are you ready? I'm going to let you start it and do the timing. And when it gets to this point, Addie is going to make the turn. You time the entire thing on the outside of the track.
No.
Stop.
6.19.
Okay. Now, I'm going to have you guys write this down here. This is applications of this data. So you said 6.19. If it truly was a constant speed car, and it traveled 2 meters, not just 1, how should that time been? Should have been twice as much, right? Now, what I want to do here is just for illustrative purposes. We're going to draw the same thing here, except now, come on, give me this is called dot diagram. You made the turn. And let's see, this was t is equal to 0. This you said was t was equal to, what did you say, about 6.19 seconds. This was 1 meter. This is 1 meter. What I'd like you to do is determine the average speed of that car and the average velocity of that car. You understand what I'm asking there? In one case, I want to know its speed. In the other case, I want to know its average velocity. Now, you have the equations above that thing, right? Speed says distance over time. And velocity says not distance, it says displacement. See if you can do that. Calculate the average speed and the average velocity over that 6.19 seconds. I want to see if you're able to do that. That's the quantitative side of those equations. Nice job. We're not going to cure COVID this day. I mean, boy, if I could, I tell you, I'd market that. All right, average speed versus average velocity. Sorry, folks, I realized I didn't give you a whole lot of space there to be able to do this work. I'm hoping that you can write that in the space that we have. Once you have it, turn to tell that person that you're sitting next to what you got for both of those values, speed versus velocity. All right. So the speed versus velocity, the speed is computed the exact same way that we did before, except now it traveled 2 meters, and that took 6.19 seconds. Now, again, it's not perfect. It should have been double the distance, double the time. But anyone have that for me? What is 2 divided by 6.19 about?
Yeah.
Just say it out loud.
0.32.
0.32 meters per second. Now, these numbers, again, should be the same, but again, we had to do a little bit of turning and whatnot like that. That's okay. There's a difference, though, between velocity and speed. Velocity, if we change a direction, which we did, our velocity is no longer going to be the same as our speed, because now we have a different displacement. Right? This number that we use there is for displacement. That's just the distance value. how far were we displaced from beginning to end? Thank you.
Square root of 2 meters.
Square root of 2 meters divided by 6.19. Now, how'd you get square root of 2? Pythagorean theorem. It did not travel in a straight line. It traveled along two legs of a right triangle. So 1 squared plus 1 squared is equal to c squared. Add them up and you get square root of 2. It traveled about 1.41 meters. Do you understand that idea that the distance, the displacement that it had was about 1.41 meters? We take this, and we take this. And now we're going to take a meter stick and place it along there, it'd be about 1.41. You understand that idea? He told me. How do you know that?
Pythagorean theorem.
Would you agree that this is a right triangle? Would you agree that those legs are right angles to each other? That distance, and you can sort of see that. If the car started there, the car ended here. The total along that, this would be the Pythagorean theorem. That's 1 squared plus 1 squared is equal to c squared. So it would be an a squared plus b squared is equal to c squared. Okay? Key idea here, folks, is that speed and velocity can be different if you have directional changes. If the direction's uniform, there's no difference between speed and velocity. Okay? But when you change, then you can get a different value. Okay? All right. Important for you guys to get that. All right. Now, before I do graphical considerations of that, because we use graphs quite a bit, I'm going to have you guys come on over to this table. Come on over. Have your seats. I'm going to showcase some of the technology that we have in the classroom to help visualize graphs in more detail. So just come on up for a minute. On your seats. I am going to show you how this software works. I'm not a big fan of these boards. I'm going to stop sharing